Okay, so today we will be talking about limitations and challenges of AI in scientific research. We'll see how data quality, its representation, and model interpretation, model reliability all go into making a good model. Why data has to be clean and why that's important. All right. So core areas of limitation and challenge as data quality, first of all. Importance of high quality, clean, and sufficient data. Data needs to be clean, quality, and sufficient. Garbage in, garbage out principle. Poor quality data leads to unreliable results, basically. Issues such as missing values, biases, or noisy data can negatively impact outcomes in the model also. Right. For data representation, choosing relevant features to represent data effectively. Feature engineering and selection play a critical role in model performance. Now, feature engineering, that's where we go into the columns of the data and pick what's most important and what's going to be most effective for training the model. And we let all the other features out. Like we drop like the columns we don't need, the data we don't need. So feature engineering goes into that. Make transformations. And I'm actually going to show you guys at the end of the lecture today a little bit of transformations and exploratory data analysis, like some of the stuff data scientists do on a daily basis, basically. I'll show you guys that. Also, model interpretation. You need to understand how a model produces specific outcomes. That's very important to understand how it produces these outcomes. Difficulty in explaining results, especially with complex or black box models. Also, model reliability, ensuring consistent and reproducible results across different data sets. The model has to be reliable, like we discussed before. Challenges with model stability when applied to new or unseen data. So the model also has to be good with new and unseen data that hasn't passed through the model or processed through the model. So a key concept here is AI and machine learning rely on not just input quality, but also proper algorithm applications, data representation, and model tuning. We discussed that before. Quality control is essential at each stage to achieve reliable results in scientific research. Always need clean quality data. The lecture focus today is identifying and addressing common issues with data and model application, understanding the impact of these factors on the reliability and interpretation of AI-based research outcomes. All right, next slide. So we have data quality, first of all. It's one of the biggest challenges, we have to verify it, it has to be consistent, it has to be complete, and it has to be timely. So, all right. So, I'll this a little bit here. So data quality is one of the biggest challenges in machine learning, and there's three like more important reasons up there. Hello, Babu, how are you doing? So 43% of data scientists and machine learning engineers say poor data quality is the biggest machine learning barrier. Is that we have poor data quality. The quality of the data is not good enough. 38% say it's the report of data availability as the second highest barrier. The data we want to train on is not available. So sometimes they go through things called data augmentation. So they make up data that can fit into the model because we don't have enough data. So we make data for it, the model to train. And 33% say they find it hard to hire data scientist talent, because first of all, it's hard to train a data scientist. it's hard to grasp the concepts of machine learning, but you guys, I'm proud, like, you guys are doing a good job grasping them, even though you're still in high school, which is really good. So that's another factor. They find it hard to hire these data scientists, and, especially here in the US, there's a very high demand for data scientists and machine learning engineers and AI specialists, but there's not enough graduates or people that are qualified for these kind of jobs. So we bring them, so they kind of like, they bring talent from overseas to fill these gaps within the market, right? But it's still there's a shortage, so it's a good career to head into. All right. An overview here. Data quality is a critical factor that impacts the success and reliability of AI and machine learning models. High quality data is necessary for accurate modeling and research results. Again, the data quality is extremely important. Key dimensions of data quality: verifiability. It needs to be verifiable, ensuring the data is credible, validated, and accurately represents the subject of study. The source of the data itself. When it comes from a government agency or research facilities like this one, is not when it comes from like some random website, right? So it needs to be verifiable. It can be difficult to achieve in some field, but it underpins the reliability of the entire study. Potential issues would be measurement errors, collectors' biases, and reporting inaccuracies. Another factor would be consistency. The data has to be consistent and standardized, right? Data must be standardized for meaningful comparisons and model integration. Examples: converting units or normalizing sample methods across multiple studies. Inconsistent data can lead to erroneous model predictions. So let's say we have like a column that's all the numbers are like 800, 700, or 1000. Sometimes we like to standardize it between 0 and 1 so the computer can understand it better. So like divided by what? Like by 100, by the whole column by 100. I'm going to show you guys some examples at the end, like I said. Completeness. The completeness of the data is important also. Having sufficient data points to cover the study or model effectively. Gaps in the data can hinder the model's ability to learn and generalize. So if we have a column that has 600 missing values or something, that's going to hinder our model training, and I'll show you guys an example. Timeliness. Data should be up to date and relevant to current study objectives. So data that's up to date, not from like 100 years ago or something. Particularly important in domains with rapidly changing conditions like climate science, because climate is always changing, so we always need new data for that. It needs to be up to date. We can't use like a lot of past data, even though they use past data in climate studies. A practical example would be climate study here. Accurate, standardized, and long-term climate records are necessary to detect anomalies and changes over time. So climate data has to be very accurate and in record. The completeness and timeliness are essential for making valid predictions. Also, in the case of predicting future weather. Importance in AI and machine learning. Data sets the trajectory of the AI model. Low quality data can undermine the model's trustworthiness and generalizability to other data sets. Quality control at the data level is essential for producing reliable AI outcomes. So again, the data has to be verified, consistent, standardized. We're not just throwing anything at the model and like training it with it, right? The data has to be clean. It has to be from a verifiable and quality source, like government sources, research facility sources, not like some random website on the internet, especially depending on how important the model you're training is or the project you're working on, right? All right. So input representation impacts here. We call for normalization or standardization, which I'll talk about right now, and input representation. Like we said here, you can take a look. See here, the This is vector embedding. So vector embedding is basically when we have a column that has text or comments, people and reviews and stuff like that. These comments and reviews are big sentences, which the computer can't read letters, right? So it goes through an embedding model and it gets vectorized. Each word in the sentence gets a number, right? So the computer can read it through. Because the computer doesn't read letters, right? So we convert them to numbers using embedding models and vectorization. So object is vectors. You know what a vector is, right? Something in like straight line, movement, momentum, right? You guys know what a vector is? Yeah. So you add it into a vector. So this vector contains, like, let's say this, we assign the word the to 0.6, 0.3 gets assigned to the word man in the phrase. 0.1 gets assigned to the word whatever words in the phrase, right? So it gets converted from letters and statements into numbers that the computer can understand. So an overview here. The way input data is represented and structured has a significant impact on the model's performance, like we said before. Proper representation ensures that the data is in a form that the model can process efficiently and effectively, right? So key concepts here we use normalization and input representation. So normalizing and standardizing the data, like I said, normalization is the process of scaling the data, often between 0 and 1, to make features more comparable, right? So if I have the numbers all like in 10,000s and 6,000, it's better that I divide them by like the 10,000 and 1,000 to make them point something. So they're all between 0 and 1. You guys get the idea, right? Computer understands it better and processes it better, right? Standardization scales data to have a mean of 0 and a standard deviation of 1 also. That's when we're talking about a statistical point of view. Both techniques help models converge faster and improve accuracy. Okay, input representation. Raw data, for example, text, images, and sound, that's called all raw data, needs to be structured into numerical forms like vectors, we said, matrices, or tensors for model compatibility. So let's say I'm putting an input of text or images or sound. Like I said, if it's text, it's going to have to be converted to numbers for the model for the computer to work with. If it's images, also it's going to get converted to numbers. And if it's sound data, it's also going to get converted to numbers in forms of what? Vectors and matrices. You guys took matrices and vectors in calculus, right? So you kind of know them already. All right. For example, images are often represented as 3D tensors, where each pixel color is encoded in the red, green, blue values, RGB we call it. So it stands here for what? Red, green, and blue values, right? So all the colors and the pictures and everything in the pixels I showed you guys in convolutional neural networks. You saw how it convoluted through the pixels of the picture. So it can pick up all this information from it, the color, the position, everything. And then it all gets converted to numbers in the computer also. So it can be processed well. All right. Common input representations. First of all, vectors. They're one-dimensional arrays represented in a set of numerical values. For example, like I said, the RGB, red, green, blue color representation gives 25, 20, 255, 255, 255 for white. So if I change this to like 254 or something, it's going to give a totally different color when I add it into the computer. All right. Matrices are two-dimensional arrays. You guys know what a matrix is, right? You worked with matrices in school, where there's two-dimensional arrays. Often used to represent structured data, such as grayscale images or spatial relationships. And then tensors are multi-dimensional arrays that can store complex data, such as multi-channel images or sequence data over time. So tensors are like a more complex form of matrices and vectors. It's a multi-dimensional array. It's called tensor. All right. So again, one of the techniques is vector embedding. Vector embedding transforms non-numerical data, like text and images, like I said, into encoded vector structures that capture semantic meaning. Like I said here, you see, I'm having a text going into the embedding model, and it's giving me all into numbers. So what's going in is like a phrase. The man went to the store, right? So it's going to take the as 0.6, let's say, man at 0.3, at 0.12, like that. So the whole text gets converted to numbers so the computer can work with it better. That's what we call vector embeddings or vectorization text. These embeddings can then be used by a model for tasks like classification or clustering. Talked about those. Impact on the model's performance. The structure and quality of input representation affect how well the model learns and generalizes to new data. So the model basically is not going to take in words and complex data right away and then give you the output. No, it's going to convert it to numbers that the computer can understand and then give you the output also. Examples include contextualizing words and languages models or tokenizing text for better inference and prediction. Like here. It gets tokenized, separated, each word gets its own number. So the computer then knows how to. They actually have libraries where they have words, and each word has its own number automatically these days. Yeah. It's awesome, actually. For a practical example, in language models like ChatGPT, individual words or phrases needed to be broken down into tokens, which are then embedded into vectors that capture the contextual meaning. Like you guys using ChatGPT, you're going to enter a sentence. How does this work or how does this happen? It takes the ChatGPT takes it, converts it to numbers, like I told you guys, and then does all of its context and processing, and then gives you the output. Right? It gets tokenized, like separated. That's what we call tokens. So here, token. So when you hear someone tell you ChatGPT can process like 1 billion tokens at a time, that means it can separate like to 1 billion words and do it can take a large amount of prompt and instructions, basically. That's one of the things you might hear in tokenization, right? To summarize, choosing the right representation for input data is crucial for achieving high model performance, ensuring the model can interpret and learn from the data effectively. Let's move on. All right. Like we had before and studied, the model structure impacts understanding the domain of the project we're working on, architecture choice, regularization and tuning. So you want to know what data you're working with, what do you want to get out of that data, what's the machine learning model supposed to do. We make our choice, of course. If it's a supervised continuous target variable, we're going to use regression to make, for example, an ad price prediction. Also categorical. Continuous here means a number. Continuous variable is a number. Categorical variable is a word or a cat or a dog or something like that. So through classification, an example is medical imaging, cancer, benign or malignant, good or bad. That's an example here. Unsupervised we talk about is unlabeled data. Supervised is labeled data, we said. Target variable is unavailable, so it's unlabeled data. So we use either clustering or association. In clustering, we have the customer segmentation example, and in association, we have the market basket analysis. Semi-supervised, we talk about categorical, target variable, classification, and clustering. The classification would be type classification, for example. Clustering would be land finding on GPS data for clustering. That's one of the uses in GPS. And reinforcement learning, like we said, there's an environment, there's an agent, and there's a reward and punishment factors. So if it's a categorical variable, which is word, or a category of something. We're gonna use classification, optimized marking as an example. Also for reinforcement target variable unavailable, we use control, driverless cars, something like that. All right. And here there's a linear regression for tumors. Do you raise your hand? This is a linear regression of tumors showing malignant and benign based on certain variables here. Okay, an overview. The structure and architecture of a model can significantly influence research outcomes and model performance, like we said. The model structure involves the interconnections, layers, and how inputs are processed to generate outputs. Talked about that. Key points to take in here. The domain or type of data plays a crucial role in selecting the appropriate model. Some models work better with specific data types and tasks. For example, linear regression, best for numerical data. Like we said, linear regression always works with numerical data best, with limited numbers of features. Deep neural networks, they're suitable, like we said, for large data sets with complex features like image and speech. So in this case, we're talking a non-neural network. In this case, we're talking a deep neural network, which is a neural network. Architecture choice also goes into that. Selecting the right architecture is vital for capturing complex patterns in the data. Example of architectures we took before, a convolutional neural network works good with images, recognition, and processing. So it works mostly with graphic data that has imagery or videos, right? And then a recurrent neural network we talked about is good for sequential data like time series and text. Talked about a recurrent neural network. And here a logistic regression, simple and effective for binary classification tasks, but it struggles with complex nonlinear data. So it can't be used for something that's a convolutional neural network is going to be used, basically. So the model complexity. More complex architectures, such as deep networks with multiple layers, we said deep networks can go very deep and have multiple layers, hidden layers. Can better capture intricate patterns, but are computationally expensive. They're expensive to train because they're more complex than the regular networks, right? Choosing the simplest effective model can sometimes yield better results without unnecessary computational costs. So you might have chosen a convolutional neural network, when it's not necessary. You could have chosen a logistic regression model because it's more expensive to train a convolutional neural network for the problem. Even though you could have chosen logistic regressions to solve the same problem, and it wasn't going to cost you as much in computation and processing prices, which is mostly on cloud architecture. All right. So regularization and tuning. We talked about regularization. It helps reduce overfitting by penalizing large weights over overly complex models. Techniques include the L1, which is lasso we talked about, and L2, which is bridge, and dropout. For the tuning, we said, we adjust our hyperparameters like the learning rate, number of layers we're going to add into a neural network, the activation function like sigmoid or ReLU. So you can go back always and change these parameters to get better results and accuracy, like we said. Tuning the hyperparameters, right? Impact of model structure and research goals. Depending on the research goal you're trying to get to, selecting an architecture that matches the data and desired outcome is crucial. Like I said, you might choose one model to train for the same problem, but you could have chosen something else which costs you less time and money, right? And everybody wants to save time and money. Some models like linear regression, they prioritize simplicity and interpretability, and that's what I'm gonna show you guys tonight. How to do some exploratory data analysis and feature engineering. And on Thursday night, I'm gonna actually train a model in front of you guys, and we're gonna see how it works. So, and it focuses on high performance with large data volumes also. Model refinements like gradient descent, hyperparameter tuning, and regularization can optimize models for better performance and generalization. Choosing and refining the model structure is the balance between domain requirements, computational resources, and desired outcome. We always put all these in mind. What's the budget the company's willing to put into training a very large model? The $80,000, like $150,000. They always try to save money in that domain too. All right. Next. Uncertainty in the input model is also a problem. Uncertainty quantification, we use Bayesian neural networks and dropout. All right. Model outputs can sometimes be uncertain due to a variety of factors. Understanding and managing this uncertainty is essential for assessing models' reliability and making informed decisions. Types of uncertainty here is the knowledge. It's epistemic uncertainty related to the lack of knowledge or information in the model. So we don't have enough data or lack of knowledge on the model, basically. Can be reduced by acquiring more data or improving the model's understanding of the domain. So let's say I don't have enough pictures to train something that detects a certain type of birds. Model on an island that has this breed like of birds that need to be taken care of because they're spreading like so wide or something, and we need a model that detects these birds. If we don't have enough pictures for the birds, we can go online and, like I said, do data augmentation. We can get more data to train the model from online sources. And there's data augmentation tools these days that make whatever pictures and whatever text you want. Awesome, actually. Example for this is a medical diagnosis that requires multiple tests or expert opinions to confirm. It can be statistical, aleatoric uncertainty caused by inherent randomness or unpredictability in the data. Irreducible because it arises from noise or variability in the measurements. So the data the data points are too far from each other, basically, in the column. Let's say I have a column of something's width, but there's very high widths and there's very low widths. So there's big variance within the data itself, right? So this is a statistical problem. Example here would be weather predictions, where unforeseen random factors can affect the outcome. So we have like random factors getting into the data, very high numbers, very low numbers. These can affect the data too, cause some uncertainty. How do we quantify? Quantifying uncertainty helps in estimating the model's confidence in its predictions. Methods for that would be confidence intervals, would be like the range and within the true outcomes is likely to lie. Probability distributions represent the likelihood of different outcomes. More techniques for managing uncertainty here would be a Bayesian neural network. It incorporates uncertainty directly into the model by estimating the probability distribution over model parameters. So using probability here. Useful for making decisions under uncertainty and providing confidence estimates. That's the Bayesian neural network. It works with managing uncertainty in a model. Dropping out also works, which is a technique to prevent overfitting. Like we said, overfitting is when the model learns the data too well. It's like someone who reads a book and memorizes each line of it, but doesn't understand anything, right? So that's overfitting, So one thing we can do is we drop some of the neurons within the hidden layer, right? You guys, I discussed the hidden layer with you guys before, right? The hidden layer can be like 300 layers or something, right? So we can choose to drop half of each layer, right? And this is something we can work on in the code, which is going to be like drop out equals 0.5 of each layer, like half of the neurons in each layer. So that reduces uncertainty, reduces computation costs, it improves the robustness of the model. Some neurons are not needed, within the model. So we drop some out to keep the model consistent and robust. That's another way of getting rid of uncertainty, right? An application of that Is understanding and managing uncertainty. It's critical in fields like medicine, finance, and climate modeling, where decisions need to be made based on reliable predictions. You know, it can affect very big things in these fields, you know, especially medicine, finance, and climate modeling. You know, if you don't have a good model that can do good predictions, reliable predictions, it can affect things really bad. Quantifying uncertainty helps in risk management, you know, getting rid of risks and while working on a project or something. You want to mitigate risk as much as you can. And planning under uncertain conditions. You know, you never know what's going to happen in the future, so it's always safer than sorry. Summary: acknowledging and addressing uncertainty in models output is key to ensuring the model's reliable and trustworthy results. Techniques like Bayesian neural networks and dropout are powerful tools for managing and quantifying uncertainty in AI. Which I know dropout is the one that's used most, because I've seen it in a lot of models of people using it. All right. So the understandability of the model also goes into play. Interpreting a black box where the yes.
Into that.
Yeah, yeah. Want me to wait for you?
Okay.
Good. So interpreting a black box would be like, you know, a black box is where data is stored and it's unorganized and it needs to be encrypted or decrypted to be understood. You guys know what encryption and decryption is, right? Deciphering something and cipher language, something like that in a black box. And you have something called explainable AI, which makes AI clear and explainable. Factors of explainable AI. Like we said here, there's an input model. There's an input, goes through a model, and we get our output. All right. Like I said here, you guys see this? Like for example, dropping out. These are the layers, right? So if I like drop 0.5 of them or something, or 0.3 of the neurons in the middle, it's gonna drop 1 here, 2 here, 1 here. So you know, all the ones that are gonna drop are like deactivated neurons. So it saves time, it makes the model more robust and more, you know, accurate. And saves money also for computation. All right. Overview here, AI models, especially deep learning models, are often referred to as black boxes. Like I said, because their decision-making processes are difficult to interpret and to understand. Like I said. This lack of transparency raises concerns. Why? Particularly when AI is applied in critical fields like autonomous vehicles. You know, you don't want a vehicle to get you into an accident because the model wasn't trained right? And medicine and finance. Especially an autonomous vehicle, you know, if you have a model that's been trained wrong, you know, and it doesn't do the right work, you can get into an accident easily because you're totally depending on the car to take you somewhere, right? That's not good. Challenges in interpreting a black box. AI models, due to their complex internal architecture and thousands of parameters, can produce outputs that are hard to explain even for their creators. Even the people that made them, you know, it can be hard for them to understand, right? An example of this would be if an autonomous vehicle fails to detect an obstacle and causes an accident, meaning an obstacle on the road. It failed to detect that this is a curb or this is a car coming in at a certain speed because it has this camera taking pictures all the time. It can be challenging to pinpoint which part of the model contributed to the error. So, you know, it's challenging. The model is too big and complex and we trained it. Which part are we going to go back to in the model to retrain and make sure that the car doesn't, you know, make accidents, right? Because that's very crucial. You don't want to drive a self-driving car and then, you know, it hits you into a wall or some other car, right? That would not be good at all. For definition, explainable AI is emerging. It's an emerging field focused on designing AI systems that are interpretable, understandable, and traceable. So I can trace where I did the mistake or which hyperparameter needs to be changed. You know, if the model gets too big, like ones for self-driving cars, these models are really big because they have to train on everything. Like this is a car, this is a curb, this is pole, this is coming at this speed. It's complex, you know, and if you do something wrong and someone gets into an accident, your company, you know, is gonna get sued and fined and all these things, you know, companies don't want. It aims to make AI models, like I said, you know, more explainable and more traceable. So you can go back and make corrections if something goes wrong. Basically, that's what we call explainable AI, XAI. Goal of this is to improve trust and safety in AI systems by ensuring their decision-making processes can be understood and validated by humans, and also readjusted for errors. Factors of explainable AI: prediction accuracy. The model's predictions need to be accurate while also being understandable, right? Balance must be achieved between performance and interpretability. We want it to have high performance and also be a well understandable model that we can go back to. Like, especially in coding, they ask that you put comments on the code. This piece of code does this. This piece of code does this. You know, and segment them in a good way where you can go back and change anything if needed. Traceability, like I said here, tracing the code. The ability to trace back how and why a model arrived at a specific output. Why did it make this mistake? I have to go back and look at it. This involves tracking the flow of data through a model and analyzing which feature or input influenced this decision. Decision understanding. The human aspect of explainable AI, which is XAI, that focuses on explaining decisions in a way that is meaningful to the stakeholders, such as users or regulatory bodies. Ensuring that people understand that rationale behind the model's decision is crucial for trust and ethical considerations. So I built a model, you know, I'm the engineer, let's say at a company, machine learning engineer. I have stakeholders, which are like the company CEOs and the people that are going to be using the model. It needs to be explainable to them, right? You're not going to use that heavy technical jargon to explain that to them, right? So you try to explain it as simple as you can, right? Methods and techniques of explainable AI is feature importance analysis, identifies which features have the most influence on the model's predictions. So if I have 4 features in a model, like width, length, height of something, I try to choose the most important ones, right? That are going to make the best predictions and leave other unnecessary features out, which I'm going to show you guys an example. Until we have 3 slides left, I'm going to get into it. But there's another method called LINE, local interpretable model agnostic explanations. It breaks down complex model decisions into simpler parts to explain how certain inputs impact the final prediction. And SHAP, shapely additive explanations, assign importance values to features to show how they can contribute to the prediction. So it gives certain features more weight than the others, right? Importance of explainable AI. It enables the identification of potential biases. Like we said, bias is an important hyperparameter we go back and fix. Errors or unjustified decisions in the AI models. It helps developers and users build trust in an AI system because they rely on it. You know, it has to be trustworthy and reliable, especially when these systems are deployed in high stakes or safety critical environments. Like I said, for the self-driving car, you don't want to have an accident. Someone having an accident because of a mistake in the model, right? To summarize, the move towards explainable AI is crucial for ensuring that AI systems are not only accurate, but also transparent, trustworthy, and ethically sound. By making AI more understandable, we can enhance safety, accountability, and user confidence in AI technologies. All right, hallucinations. What are hallucinations? How do they happen? How can they be prevented? RAG, which is retrieval augmented generation. Take a look at this. So what's a hallucination in the model? You guys know what hallucination is in real life? Hallucinating, like, you know, you don't know what's happening, what's, you know, can't interpret anything of it. Hallucinating, basically, a human hallucinating, it's the same kind of thing, right? Hallucinations in AI refer to instances where models generate false, misleading, or non-sensational information, you know. The information the model produces has no meaning, basically, you know. It's misleading, it's false. That's called a hallucination in AI models. This phenomenon is especially common in generative AI models, just like Gemini and ChatGPT, all the models we have today. Where they produce irrelevant or factually incorrect outputs. You know, the output it gives is incorrect. It's irrelevant to what you're asking it. You know, that's another hallucination problem. Example is an AI might incorrectly generate historical facts or make up data that was not part of the training set. That's a hallucination in an AI. How do they happen? Like I said, data quality is not that good, and its completeness, right? We need good data, good quality data. Hallucinations often arise due to a lack of quality or diverse data in the training set. The data is not of good quality, like we said. If the model hasn't been trained on comprehensive or balanced data, it may generate inaccurate responses. That's another problem with hallucination. Overfitting, like we talked about, you know, the model learns it too well, but can't work good on testing data, right? If a model becomes too focused on specific patterns or biases in the training data, it may generate outputs that don't generalize well with inputs. That's another form of hallucination. So it all comes back to the model not giving you what you want, basically. You know, give something completely different than when you ask or what the input entitles, right? The model's complexity and size. Large models have more parameters and complex internal structures, making them more prone to generating unpredictable outputs because they're too complex. Lack of contextual understanding, you know, you need to give the model context of what you're working on, especially like when we're working with GPT. I'm going to show you guys an example. Heading into the final part of the lecture, especially if the context is nuanced or not explicitly present in the input data, right? How can hallucinations be prevented? Like we said, regularizations, you know, regularization techniques help reduce overfitting and can prevent the model from making extreme predictions, going too extreme. Quality data and curated data sets, using quality data can prevent hallucinations. Ensuring the model is trained on diverse, high quality data relevant to the intended application can reduce hallucinations. Setting clear constraints, you know, having standards and boundaries. Define specific requirements and exclusions for the model. For example, instruct the model to rely on verified scholarly sources. You know, you don't want to get random data from anywhere when generating research content. User guidance. Users can provide detailed prompts and explicit instructions to direct the model's output more accurately. One of these is retrieval augmented generation. Definition would be RAG. Its synonym is RAG, R-A-G. It's a method that combines the strength of language generation models with retrieval mechanisms from a trusted knowledge base. You were asking about that last lecture at home, right? How the models bring in new data. Yeah, this is the method. Like retrieval augmented generation. It fetches the data from newer sources, which is a new technique because back in 2001 and 2002 or something, the model would only know knowledge up to 2002 and 2001 when it's trained, right? But since we have RAG now, which is retrieval augmented generation, it does that for us. It brings it from trusted knowledge bases. Instead of relying solely on its internal knowledge, like I said, but which it was trained on, the model retrieves information from external databases, providing more accurate and reliable outputs, right? Retrieval augmented generation. Application for this would be RAG can be implemented in AI applications to reduce hallucinations, of course, by incorporating real-time information from curated sources, which is the newest technique used in AI, RAG. particularly effective in specialized fields like medicine, finance, and academic research, where the stakes of incorrect information are high. You know, any little bit of incorrect information in these fields can lead to, like I said, bad results and bad predictions. To summarize, hallucinations present a significant challenge in AI applications, potentially undermining trust and utility of the technology. We want a technology you can rely on. The people who invested in it want a technology that can be relied on, right? You don't want something that's giving you out very bad outputs or bad predictions, right? Because it's very crucial. That's where RAG came into play. Like I think they made it in 2003, 2002, 22 or something like that, 22. Hallucinations present a significant challenge in AI applications, potentially undermining trust and utility of the technology, like we said. By applying strategies like RAG, retrieval, augmented generation, and using high-quality data, AI developers can mitigate hallucinations and improve the reliability of the AI outputs. So getting rid of hallucinations, right? Okay. Current understanding of bias. You guys know what bias means, right? I'm biased towards something, towards a certain group of people, whatever it is, like you're biased towards something, towards a certain group of people, you're biased toward, you like this certain group of people better, you hate this, this is what biases me in real world. But here, I'm gonna say bias in AI and scientific research. While the term bias in neural networks traditionally refers to a mathematical constant, because we use bias in the model, the word bias, it means a mathematical constant here. Bias in data science refers to unfair prejudice and distortion of results, whether intentional or unintentional. So unfairness, basically, in the model stream. Bias can greatly impact the reliability and fairness of AI models, particularly when used in sensitive applications like healthcare, hiring, or criminal justice. Like let's say in healthcare, it can be biased towards a certain group of people. In hiring, it can be also biased. The model can be biased towards a certain group of people, or in criminal justice. Same thing. So the bias in data here we're talking about bias in data. It originates from the data itself due to its composition, quality, or how it was collected. Certain groups, situations, or scenarios are underrepresented or misrepresented in the data set. The model's predictions will reflect these variants, right? So I have a model I trained on certain groups of people, but I used let's say, don't get me wrong here or anything, but it takes in data from let's say white population, from black population, from this population. It used a certain population more than the other. So this is a form of bias in data, especially in statistics and gathering information. Algorithm bias refers to biases introduced in the way algorithms prioritize information. It can happen in the algorithm's function, loss function, its hyperparameters. I might choose an algorithm. I might be using a certain algorithm all the time. I'm biased towards this certain algorithm, but I can use a different algorithm, basically. Selection bias occurs when the sample data used to train the model is not representative of a general population or target group. It doesn't have enough, for example, a medical diagnosis AI trained primarily on male patients may not perform well in diagnosing female-specific health conditions. That's another form of bias, right? I didn't get enough information on the female. Let's say female bodies have different composures sometimes and with disease. Same thing with male bodies. I got more information on male bodies, but not on female bodies, right? So the diagnosis doesn't go well. So right now I'm biased towards males, right? In my research and in my model. No, it's it has to be balanced, basically. Confirmation bias. Confirmation bias happens when AI systems influenced by existing beliefs or dominant trends in the training, reinforcing stereotypes or common misconceptions. It's basically confirmation bias is like saying, I have an idea, this is my narrative, this is what I believe, you guys are gonna believe it too, because it's awesome or whatever, I'm trying to confirm it however I can. Because I believe it's true, so I'm trying to confirm it to you guys as much as I can. This is confirmation bias. No, you're not supposed to do that either. Example here, if a language model is trained on biased sources, it might overemphasize the source's viewpoints, an unbalanced or biased content. It has this idea which it's stuck to, and it doesn't want to change it, and it's trying to force it. You know what I mean? No, this is called confirmation bias. I'm trying to confirm what I believe in to others forcefully, in a forceful way, basically. Something like that, you know what I mean? So that goes to confirmation bias. We want to get rid of that too. Measurement bias also is a problem. It arises from the errors or inconsistencies in how the data is measured or recorded. I didn't, for example, if a sensor used a scientific experiment not calibrated correctly, the AI model might learn from flawed or skewed data, right? The measurement tool itself is biased. It's not correct. So that can lead to measurement bias in bad data. Preventing and addressing bias. Ways to do that is data diversification, having diverse data, balancing the data, like women, men, female, male and female, have them equally represented in the model or the data. Algorithm design, use fair, in the algorithm itself, use fair constraints to train your model. That's when it comes to the algorithm. Regular auditing, perform regular audits and evaluations of the model's outputs to identify and address emerging biases also. Domain expertise, involve domain expertise to bring the experts in, You always go back to the experts in the field, right? Also, that's another way to get rid of bias in training data. It's a big problem, actually, when you're biased towards a certain group or a certain type of data or this or that. It kind of doesn't make the training of the model that well. We always need a model that's balanced and fair, basically. To say, bias is an AI critical issue that can lead to unfair, inaccurate, and harmful results. Being aware of different types of biases and implementing strategies to address them is key to creating trustworthy and equitable AI systems. For our last one here, last slide. And then we're going to get into training. I'm going to show you guys some examples of what we do before we train a model. Yes. Yeah. So, for last slide, we're going to talk about the importance of domain knowledge, accuracy, what data is obtainable and trustworthy, model limiting assumptions, right? So domain knowledge, what does that refer to? It refers to specialized knowledge or expertise in a particular scientific or professional field. I'm professional and specialized in a certain field, basically. I know a little bit about this field, a little bit about this field, but I specialize and professionalize in one field, right? Just like, let's say I specialize in data science. This guy specializes in medicine. He doesn't know everything about data science, and I don't know everything about medicine, right? Like that. In the AI, domain knowledge is crucial for framing problems, selecting appropriate features, and validating model outputs. Benefits of domain knowledge in AI. It improves model accuracy. Like we said, we're always looking at improving the model's accuracy. Domain experts can help identify the most relevant features. That's where the experts that have been there for a while doing this, they find the most relevant features in the data set or in the data and ignore unimportant outliers, like features that are not needed. We drop these columns, we don't need these columns, it's not important for the prediction or the output of the model. And it ensures the model is focusing on the right data. Example of this would be meteorologists would understand which atmospheric conditions are critical for weather forecasting. That's an example. Determining trustworthy data sources, domain experts are best positioned to determine which data sources are reliable and has clean data. right? Incorporate multiple viewpoints, right? Can reduce bias, like we said, and improve the objectivity of the data set. Understanding the limitations and assumptions in the model. Experts also can recognize the limitations and the changes assumption in the model, or if in its reliability and fairness. Example of this would be assumptions around fairness and equity, and models may require nuanced understanding that goes beyond mathematical quantification into philosophical and ethical considerations. Role in framing the research problem. Domain knowledge helps accurately define the research problem and set realistic goals for AI implementation. You don't want to do fantasy stuff. You want to do real world stuff, right? You don't want to do stuff out of fantasies. Experts provide insight on how AI models should interact with domain-specific factors and constraints. Let me just summarize here. Involving domain experts, subject matter experts, which are the guys who are like in the industry for 20, 30 years, let's say. Involving them in AI model design is essential for ensuring the models are both scientifically accurate and contextually relevant. Without domain knowledge, AI model risks being incomplete, biased, or misaligned with the actual goals. That ends our slides for today, and I'm going to show you guys some examples. Yeah. All right. So, since this is an AI for science class, can't go on without using large language models, right? So here, I'm using ChatGPT. First, I'm asking ChatGPT, I'm telling you what, I'll be doing some EDA, which is exploratory data analysis, on the iris flower data set. It's a data set very famous that students get trained on. It's for flowers, 3 types of flowers. It has to predict which type of flower it is, right? It's called the iris flower data set. From the scikit-learn library, extract the library and show first 5 rows, right? So coming down here gave me, let me work on this one first. So I actually asked it to create a new column and call it species by name column for the iris data set. Here, I'm going to show you guys. Copy this. Go into our Jupyter notebook. I actually had it here already. You guys can see well? See well? All right. Shift and enter. See here? Oh, I don't want this print thing because I want it in the table form. So I'll get rid of the print function here. So I'm using the head method on this iris data frame. All right. First of all, I imported pandas, the pandas library, and from sklearn library datasets, I loaded the iris, the flower irises. I stored it in this variable, right? Iris, to make it short on myself. I created a data frame with pandas, PD here, right? I added a target variable, which is the one we're trying to predict here, which is the species, and made it the target variable. And I mapped each species 0 to Setosa, 1 to versicolor, 2 to virginica. Again, like I said, we need to be working with numbers, right? So then I used iris data frame dot head function. The head function will show me the first 5 rows. See this? It's awesome, right? So what features do we have here? Since we're doing feature engineering, like I said with you guys. Sepal length, sepal width, which is the shape of the flower, right? The sepal and the petal of the flower. The petal's length and the petal's width, and the species. But the first 5 rows here are all showing Setosa. So they're called Setosa, versicolor, and virginica. So first thing I said here is display the first 5 rows using the head function. If I want to display the last 5 rows or something, I will change this to tail function. See, it has 150 rows, so it got me the bottom 5 rows. And in the bottom here, I can see mostly their virginica, which is mapped to the number 2. Virginica, right? Just an example to show you guys here. See what I'm telling ChatGPT here? Next cell. So I'm letting it know I'm working in a Jupyter notebook. So I'm telling it next cell, code to drop the petal width column. Right? I have the petal width column here. But let's say I don't want it. It's not necessary for training the model, or it's not a necessary feature. It's not a necessary feature that we need. So I want to drop it. So I'm asking ChatGPT here, go to drop the petal width column. So here, it's taking iris.df using the drop function, and we chose the petal width column. Axis 1 is the axis of the columns, and in place true. So I'll take this piece of code here. This is the next cell. Add it, paste. But I want to get rid of the print here because it prints it out weird. I don't know why. Just use the add function. Here. The petal width doesn't exist anymore. Right? So we decided it's not an important feature. I'm just giving an example, right? But it is an important feature. We're going to use it on Thursday. So I dropped it. I don't need it. Right? It's not an important feature training the model, so we got rid of it. So here we're left with sepal length, sepal width, and petal length. Right? Here, look what I'm telling you. Now, next cell. Multiply sepal length and sepal width columns and create a new column, which is the area of their multiplication. Width times length is area, right? So, and call it what? Sepal area. This is what I told them to do in the next cell, right here. So, basically, called a new sepal area column, and the new sepal area column equals the sepal length column times here the sepal width column out of the iris data frame, right? Here. And then we're going to show the head again, which is five top rows. I don't like this print function. Here, sepal area. See that? It's the multiplication of the sepal width and sepal length. See the power of this stuff? 10 years ago, you had to sit down and actually like do a lot of debugging, do a lot of coding, do a lot of this, do a lot of that. But this can do it like instantly. It's amazing, actually, really. See, sepal area came out to us. I named it here and said it's equal to the multiplication of these two columns. And it gave me this, right? It's amazing. More feature engineering before we can start training our model. This is stuff we do before we start training the model, right? So I'm asking here, next cell, select first row and second column. I'll actually skip this one. So I said next cell, fill the sepal length null values with the average of the column's values, right? If there is null values in the sepal length column, I want to fill these with the average values of the sepal length column, right? Here. But there are no null values, so it's going to print out an error. But I'm just to show you guys some of the things we do. The data scientists do for training the model. Okay. Gave me an error here because there are no null values, basically. But this is one of the things we do. There's empty, let's say we're working here on the sepal length here. And these two rows are empty. Right? It's going to take the average from the whole thing, from the whole column, and fill these two empty cells with it. But we don't have any empty cells here, so we're going to move on. More to do here. Like I said, next cell, drop null values from the width column. It's the same thing, same idea. Right? Next cell, find average value of the petal length column. I want to see what's the average aside the petal length column. What's the average value? So I take this here, paste it here. You guys can see here, iris data frame that shows it, right? these square brackets, petal length column in centimeters, that's what it's named here, right? And dot mean function, using the mean function, multiplying it by the mean function. And then I'm printing out this phrase here, average sepal length, right? Let's see here. Gives us the average in the sepal length, right? Which is 3.75. So you're getting an idea of what's going on in your data first before you train the model or anything, right? Moving on. Next cell, find the top 75th percentile in petal length column. You guys took statistics, right? You know the 75th quantiles, 25th, the 50th, and 75th. Let's see what the 75th percentile in the petal length column is, right? Take this. Shift enter, it's 5.1. See how fast it does it for you? Imagine something with a million rows. You're not gonna go through these million rows, like, you know, this is basically a senior data analyst stuff, like, because data scientists are the one that use Python the most and do these kind of things. This is for data science and senior data analysts. But imagine having a million rows, and you want to see you want to get this result in a second. See how fast Python did it with a little like code? That's it, right? We use the quantile function, and we added the 0.75, which is the 75th percent. All right, next cell, I ask you to graph all 3 flower types in bar chart to see their quantity. I want to see how much they are to each other. But here they have an equal distribution, but it's gonna show you guys here. Let me show you. First, I import the matplotlib library. Like we said, it makes visualizations and graphs. Import it and put it in here. All right. Look at this. Wonderful, right? But since we have them in each, I have 50 of each, so it gave me here 50, 50, 50. See here, I shows the plot kind is bar, color, light blue, first one, light green, and salmon here. I can change these, brown. Let's say just blue here. See that? You can change things around. The figure here also gives us the figure size for the first line here. I can change it to be an 8 times 8 or something, right? Got a little bigger, right? Just some of the little things we can change here. The X label, which is on the X axis here, they're called species. I can just change it to, see, it came out here as species. I can change it here to like just flower types or something. See, change here. Gives you a good idea of what you can do with this stuff, right? It's very powerful, very, very powerful. All right, so this is for bar charts to show me that they are all 50 and equal in number here. I have 50 setosas, 50 versicolors, and 50 virginicas, right? Moving on, I ask here, next cell, graph a pie chart of the 3 flower types. So I want to see the quantity again, but in a more accurate way. So you guys know what a pie chart is? So, okay, awesome. So I ask it to make me a pie chart right here. Did you guys see how I gave it context from the beginning? It knows what columns are in there. It knows what's this. It knows what's that. You have to give it as much context as you can to be able to get results like these, right? All right, so we're gonna make our pie chart. Awesome, right? See, pie chart here. Also, I choose the light blue, light green, salmon colors. See, yeah, actually, it shows it for me. So we have here the setosas are 33.3%, the virginicas are 33.3%, and the versicolor is 33. See, this is called data mining, or it's like mining into the data to know what's in it before you train the model, before you do anything else, right? You want to know what's in the data, what you're doing, and these are the methods we use, right? Until now, it's clear for you guys, right? That we need to have quality data. We need to choose the right features, drop the features we don't need, make transformations, make multiplications, add new columns, right? All right. Last thing here. Actually, the best. Another example. Scatter plot, petal length versus sepal length, right? I want to see how they correlate to each other. If the increase in one of them causes a decrease in the other, right? So I make a scatter plot here. So here, all three types, each one in its color. Satosa gave it a purple color, first color gave it this color. So we can take a look here at, if the petal length in Virginica, so this is pure data analysis right now, right? If the petal length in Virginica is causing, a sepal length increase in the Virginica also, which we have it in yellow, we can take a look at the versicolor, we can take a look at the Satosa, right? It's awesome, right? It's a very powerful tool. And lastly, which is like the one that, makes a lot of, our correlation examinations, is called a pair plot. And we need to get the Seaborn library for that, which is the most powerful and most dynamic library for visualizing data. It's called the Seaborn library. I imported it as SNS and I started using it here. So I see SNS dot. The pair plot is part of the SNS library, right? So I summon the pair plot and add everything here, and let's see what the pair plot shows us. Oh, Seaborn is not, it's not installed on Jupyter, so I have to install it. So the way to do this is %pip install Seaborn. Move it, here you go. See, this gives you an overview of everything, right? So I want the sepal length versus sepal length here. I can show you a correlation here, right? I want to see sepal width to petal length. Come here, petal length, sepal width. So it's this one. You guys see how much you can carve into this and like see what data points matter, what data points don't matter. These are very powerful tools. Make a graph like this, I can show you everything in the data, right? One last thing here, I might show you guys. One of the little things we also do, drop null values and non-applicable values and print out row and column count to see if there were any non-applicable values, right? So what I do here. This. This. So basically before and after, right? This is before I drop non-applicables, and this is after I see non-applicables, right? I just made another version here of it to see how many non-applicables we had in the data set. So we can adjust that and address it if it's an issue, right? But I found out that before dropping the non-applicables, I had 150 rows and 6 columns. And after dropping the non-applicables, I still have 150 rows and 6 columns, which mean I didn't have any non-applicables in this data set, right? And that's a little bit of the stuff they do for training a model, right? Take a look at the data. We do all this stuff here. Like I start from the beginning here. bring in the data set, right? I dropped the pedal width column from here because it's not necessary, so I'm doing some feature engineering because the other features are more important, right? And so on. Yep. Next Thursday, I'm gonna do the stage after this, which I showed you guys some of the things we do before we train the model, right? Next Thursday, I'm gonna train the model and I'm gonna put these numbers in. I'm gonna put random numbers in like this from these columns, right? We're gonna train a model and we're gonna put these random numbers in, right? 5.1, 3.5, and 1.4, and something else. And then it's gonna tell us, is it a Virginica flower? Is it a simple width flower? Is it this flower, right? It's gonna be awesome. You guys are gonna like it. And it's not gonna be the first model I'm gonna train for you guys. I might go into training the model for classification of tumors, see if it's a good tumor or not also. I'll bring that data set in and I'll work on it with you guys. But you guys get the idea, right? So this is what they do basically, you know, multiply columns together, create a new column, drop one column, drop the empty cells, multiply this by this, do this by that, look at the graphs, see what the data falls, what it does. You know, this is pure data science right here, you know. So yeah, I just wanted to touch base with you guys on this. And Thursday, I'm gonna train this model. I'm gonna train this data set to predict for you guys, whether in front of you guys also, using ChatGPT, the power of ChatGPT, and see this stuff. I could have sat a whole day, you know, coding it and debugging it and going back here to see if there's a column missing, if there's a bracket not closed. See, all this stuff matters, but this stuff makes it so easy these days. Like, you know, you finish it quick, but you know, it's just amazing. And this ends today's lecture, guys. I hope you liked it, and I'll see you guys on Thursday. And we'll train this actually on to see what type of flower we have. We're gonna put in these numbers into the model. We're gonna fit it. We're gonna train it. We're gonna graph back propagation. I'm gonna graph actual versus predicted, and I'm gonna show you how it all works into the model, so that everything we've been saying falls into you guys, and you know like how it's going into training the models. Thank you guys, and have a wonderful night. I'll see you on Thursday.
Thank you.
Thank you.
That's the paid version of ChatGPT you have?
What?
Is that the professional version or whatever?
Well, the professional version, they give you 20 to 30 prompts a day, every 4 hours, I think. But the professional version, you pay $20 every month.
Oh,
And Google's Gemini also, which is as powerful. I think it's as powerful as ChatGPT.
that's free, right?
They give you 1 month free.
Oh, Google?
They give you 1 month free, but then they start charging you $20 every month.
Oh, they don't.
They're gonna start charging $100 on this stuff
Yeah,
every month, like, because it's gonna be very, very sophisticated in what it does, you know.
sure.
And it's gonna be crazy, but you know, people are gonna
They
love it.
hope other people compete, so the price.
Oh yeah, absolutely. You have more models being made right now. You have Claude, you have Gemini, you have Llama from Facebook.
I think it's going to be like one of those things you have to have it, like a
Oh,
cell phone.
yeah, absolutely. Yes.
Crazy.
It is crazy, right?
Thank you.
Yeah, no problem. So I'll see you guys on Tuesday.